Jupiter is the kind of planet you think you know. Biggest in the solar system, striped with clouds, famous storm, 95 moons, done. Textbook stuff. Except right now, nearly everything we thought we understood about this planet is being rewritten. The storm is dying. The planet itself is the wrong size. Its magnetic field is doing something nobody can explain. And the spacecraft responsible for most of these revelations is running out of time. The Great Red Spot has been swirling in Jupiter's southern hemisphere for at least 190 years. A storm wider than Earth, with winds blowing over 400 kilometers per hour, trapped between two jet streams moving in opposite directions. No solid surface to create friction. For centuries, it just kept going, and we assumed it always would. It won't. In 1979, Voyager 1 measured the Great Red Spot at about 23,300 kilometers across, roughly twice the diameter of Earth. By 1995, Hubble measured it at 20,950. In 2009, 17,900. Starting in 2012, amateur astronomers noticed the shrinkage accelerating, around 930 kilometers per year, and the shape shifting from an oval toward a circle. Today, it measures roughly 16,000 kilometers, about 1.3 times the width of Earth. A team led by Caleb Keaveney at Yale published a study in Icarus in 2024, offering a compelling explanation. Their 3D simulations showed the Great Red Spot has historically been fed by smaller storms. These transient anticyclones would drift in, merge, and inject energy back into the system. Like a fire that stays alive because smaller fires keep merging into it. The problem is, those smaller storms have become less frequent. The Great Red Spot is starving. Then came the Hubble observations from late 2023 into early 2024. Over a 90-day window, a team led by Amy Simon at NASA's Goddard Space Flight Center watched the Great Red Spot oscillate, not drift, oscillate. It was squeezing in and out on a 90-day cycle, pulsing like a stress ball. The storm's core brightened when it expanded and dimmed when it contracted. Simon described it as jiggling like a bowl of gelatin. When asked for a hydrodynamic explanation, she was blunt. There isn't one yet. So the most iconic storm in the solar system is simultaneously shrinking, starving, and pulsing. And we don't fully understand any of those three processes. Some scientists believe it will stabilize at a smaller, rounder shape. Others are less optimistic. At the current rate, it could become unrecognizable within a few decades. Now zoom out and look at the planet itself. In February 2026, a study published in Nature Astronomy delivered a correction that means textbooks need updating. Jupiter is smaller than we thought. The equatorial radius is about 4 kilometers less than previous estimates, and the polar radius about 12 kilometers less, both narrower and flatter. Those old numbers came from just 6 measurements taken by the Voyager and Pioneer missions in the late 1970s. 6 data points for the biggest planet in the solar system, and they didn't account for Jupiter's powerful winds, which push the atmosphere outward at certain latitudes and compress it at others. The new study used 24 high-precision radio occultation measurements from Juno, combined with wind data previous missions couldn't capture. A few kilometers might sound trivial on a planet with a radius over 70,000 kilometers. It isn't. Jupiter is the reference standard for modeling gas giants across the galaxy. Every exoplanet classified as a hot Jupiter or sub-Jupiter is compared to ours. If the template is slightly off, every comparison carries that error forward. While Juno was redefining the planet's shape, it was mapping something far stranger beneath the clouds. Jupiter's magnetic field is about 20 times stronger than Earth's. But unlike Earth's relatively tidy dipole, Jupiter's field is lopsided, complicated, and in one location, genuinely bizarre. Near the equator sits what scientists call the Great Blue Spot. It's not actually blue, and you can't see it. The name comes from magnetic field maps, where south-oriented flux is colored blue. This patch of intense magnetic field functions almost like a second south pole poking out from the equator. Juno's targeted flybys revealed in a 2024 Nature paper that an atmospheric jet runs through this region and fluctuates on a 4-year cycle. That fluctuation suggests wave-like behavior deep inside Jupiter's metallic hydrogen core, thousands of kilometers below the clouds, where the atmosphere transitions into a liquid so compressed it conducts electricity like a metal. Whatever is happening at that boundary is shaping the anomaly we observe at the surface, and we can only infer the mechanism from its effects. The poles are no less strange. Before Juno, no spacecraft had looked directly down at Jupiter's poles. At the North Pole sits a central cyclone roughly 3,000 kilometers across, surrounded by 8 smaller cyclones, each between 2,400 and 2,800 kilometers wide, larger than Australia. The South Pole has a similar arrangement, with 5 surrounding a central one. Years of tracking revealed their dynamics. Each cyclone drifts toward the pole through beta drift, the same mechanism that moves hurricanes on Earth. On Earth, hurricanes weaken before reaching the poles. On Jupiter, they don't die, they cluster. When they get close enough, they bounce off one another like springs in a mechanical system. The competing forces between inward drift and mutual repulsion create a stable, slowly rotating ring that has persisted for the entire duration of Juno's mission. And when scientists examined the central cyclone in microwave wavelengths, it nearly disappeared. Its subsurface structure is fundamentally different from the storms around it, and no one knows why. Juno also turned toward Io, the most volcanically active body in the solar system. During a flyby on December 27, 2024, it witnessed the most energetic eruption ever recorded there. A hotspot larger than Lake Superior, blasting out eruptions with 6 times the energy of every power plant on Earth combined. When Juno flew past again on March 2, 2025, the eruption was still going. By combining infrared and microwave data, the team discovered that beneath Io's cooled crust, at every latitude and longitude, still warm magma flows hadn't yet solidified. Io isn't just volcanic on the surface, it's molten underneath, everywhere. All of this came from a spacecraft designed to last 20 months. Juno arrived at Jupiter on July 4, 2016, armored in a titanium vault to survive the most punishing radiation belts outside the Sun. Its camera was built to endure maybe 8 orbits. By orbit 47, radiation was corrupting nearly every image. The team tried an experimental fix, cranking the heater to maximum and slowly cooling it, a process called annealing. It worked. As of February 2026, Juno had completed over 80 orbits and was still transmitting. Its official mission extension expired September 30th, 2025. The same day, the United States government shut down. Juno was zeroed out of the proposed 2026 budget. For weeks, nobody could confirm whether the spacecraft was still active. It survived, but its future remains uncertain. Scientists requested a 3-year extension to bridge the gap until Europa Clipper arrives at Jupiter in 2030. Without it, there will be years with no dedicated spacecraft at the Jovian system. That gap matters because Jupiter is not sitting still. The Great Red Spot is changing shape in real time. The polar cyclones are drifting. The magnetic field is evolving. Io is erupting with violence we've never documented before. The planet we put in textbooks 50 years ago, with its neatly listed radius and its seemingly permanent storm, that planet doesn't quite exist anymore. We spent centuries looking at Jupiter through telescopes, and assumed we were seeing something stable, a giant with a famous spot. What Juno showed us is that the throne is shifting, the crown is shrinking, and the king's own body is a different shape than we measured. Jupiter doesn't care about our textbooks. It never did. It's been changing this whole time. We just finally got close enough to notice. Thanks for watching, and I'll see you in the next one.